As I mentioned last time, we didn't get very much done there on the first day. We're going to kind of go back to chapter one here during discussion and kind of talk about a few things that I think is important from it. Again, the notes are pretty much filled in. Some of the notes we actually sort of covered just now, actually, with scientific notation and kind of punching into your calculator, and some of it's math. But I did want to touch upon just a few things in here. Um, that it's in the notes and you're responsible for. So let us get going on that there. So again, we may go through some of the stuff a little quicker. Again, you are responsible for it on this one, but some of it is really, I think, just some review of some math stuff. And again, it's all filled in for you. So if that's helpful, that will help you with that. Let's see here what we got going here. All right. So obviously, when we talk about chemistry in this chapter, it's going to talk a little bit about chemistry, some things about matter and stuff like that. And again, the rest of it, part of the chapter, if I'm not mistaken, is sort of how to study chemistry as well, which obviously you might want to look over. But again, towards the middle to the end of the chapter, I believe, starts talking about sort of how to study about chemistry. Also, again, like I said, some math review and a little bit about calculators, since we're talking about calculators and how to punch things in properly. So again, you should obviously read chapter one, you're responsible for it, but it does have some good pictures and stuff like that to help you if you are struggling with your calculator. And again, I can help you with that as well during discussion or whenever to help you with that. Obviously, in chemistry, it really does deal with sort of matter and basically the states of matter and how things change. So obviously, a lot of analysis is done when we collect samples, for example, in forensic science, and chemistry really does touch all aspects of sort of life. There's food chemists, there's chemists that, take care of like, health and beauty type stuff. Obviously, there's science chemists, if you will, does works on obviously medicine and those type of things. So it really does sort of cross over into a lot of areas of life, chemistry. Um, but the main thing that we sort of study in chemistry a lot of times is matter and the reactions of how matter changes, and what basically matter undergoes. So, pretty simple definition of matter is pretty much anything that has mass and occupies space. So that's pretty much everything, is considered matter. It's all around us, obviously, in different forms. And a lot of times when we talk about matter, we talk about it in chemistry. Specifically, we like to look at the different sort of states of matter. So oftentimes when we talk about matter, we talk about sort of different states of it, the states of matter. And the three common states of matter that we oftentimes deal with a lot in chemistry is solid, liquid, and gas. And a lot of what we sometimes will study in sort of chemistry is sort of what happens as we go from one state to the next. Yeah, you're tech. I'll put it this way: you're technically responsible for all of what's in chapter one. Again, to the middle to the end is a little bit of what we've been talking about. So again, a lot of it's sort of math. So you are responsible to know how to do some of that math stuff that's in there, and obviously how to punch things in your calculator correctly. So, the sections are on the syllabus for sure. You're responsible for what we're talking about now during here discussion. You're responsible for sure. But in one state or another, there might be a direct question on like, what's 6 divided by 3 or something like that. But obviously the math part of it and being able to punch it into your calculator, things that you do need to be able to obviously do. So a lot of what we deal with is really the sort of changes in state is what they're referred to. So when we have things that are in the solid state, for example, usually things are packed in pretty tight to one another in the solid state. When we get to the liquid state, things are relatively still close to each other, There's a little bit more room for movement. That's why when we think about liquids, they're more fluid, right? They're able to kind of move back and forth and pass each other. And when we get to that gas state, pretty much everybody is broken apart from one another. They're flying around, pretty much detached from everything. So these are the three sort of states that we deal with a lot in chemistry. And there is names that go with sort of these transitions. As we go from solid to liquid, that's the process of melting. We go from liquid back to solid, that's the process of freezing. We go from liquid to gas, that's the process of evaporation or vaporization, some people call it. Going from gas back to liquid, that's the process known as condensation. Going from solid, skipping the liquid phase to gas, that is sometimes referred to as sublimation. And going from gas, skipping the liquid phase, that is what is known as deposition. So these are the processes that occur as we go from basically one state to the next. And that's something that we study a lot in chemistry. And what usually happens a lot of times as we go from, say, these different states is as we go from solid to liquid to gas, we have to put heat and energy in to do that. And that is what is sometimes referred to as an endothermic process. And if you just think about it, if you take an ice cube, for example, it's going to pick up heat and energy from the surroundings. It's going to start to melt. You get liquid water. Once you have liquid water, if you continuously heat liquid water, you get steam, which is gas. And those are all processes where we put heat and energy in basically to do that. And that is what is referred to as a endothermic process when we put that heat and energy in. Opposite is true if we go from gas back to liquid, back to solid. When we do that, that's basically when heat and energy needs to be removed. And that is what is sometimes referred to as being exothermic. Exothermic is when we remove heat and energy. So if you think about it, if you have a bunch of gas molecules that are flying around, they're pretty high in energy as they're flying around and moving around. So if we remove energy, they're going to slow down. And as they slow down and they come in contact with other molecules, they no longer have enough energy to escape each other. And they kind of cling to each other and they drop into, say, the liquid phase. Then if we continuously remove that energy, they will clump together even more and go into basically the solid phase. So same idea, if you take, say, liquid water and you want to make ice cubes, right? You put it in the freezer. When you put that in the freezer, you're essentially removing energy from the water molecules and they go from the liquid state to the solid state and they start to freeze. So sort of the changing of state in terms of matter is something that we deal a lot with in chemistry. Sort of the energy change that accompanies all that, we basically deal a lot with. Obviously, as it says on this slide, structure, properties, reactions, how things behave when they react with each other are all things that we see a lot in chemistry. Any questions on that there? And as I mentioned before, matter is just basically another word for substances that make up our world. These are all sort of examples of matter. So water, for example, an antacid tablet, doesn't say that right, oxygen that we breathe. So you can see also these things are all in different phases. So an acid tablet, that's a solid thing, right? Water is a liquid, oxygen is a gas. Oxygen's O2, right? So matter, it does come in all forms. It could come in all kinds of states. It doesn't necessarily have to be one versus the other. Chemicals are substances that have the same composition and properties no matter where you find them. So for example, if we had something like water, which is H2O, it always has basically the 2 goes for the hydrogen. And if nothing's written there, It is assumed to be 1, and it goes to the oxygen. That means basically in water, we have 2 atoms of hydrogen for every 1 atom of oxygen. And that's why water looks like this, and we'll learn how to draw it and all that later on in the semester. But basically, this is basically water, no matter where you get it, no matter what they charge you for that water, bottled, non-bottled, from the tap. Fundamentally, the water part of it is all the same substance. It always has the same composition. Water is always sort of that ratio there. If you got carbon dioxide gas, CO2, it's basically 1 carbon atom for every 2 oxygen atoms. And again, it's always going to be really that, that composition. Substances are made by chemists that we use every day. Substances is, it could be a pure substance. It could be a substance, could be a mixture as well. And a mixture is basically multiple things together. Toothpaste, for example, is an example of that. And here again, it's a table from your book that talks about different chemicals that you find in toothpaste and sort of their properties. And you can see really toothpaste is a mixture of a bunch of substances. So we could have substances that are pure substances. So for example, if we have something like water by itself is a pure substance, is one sort of definition of it. If you take something like sodium chloride, which is NaCl, it's a fancy way of saying salt, also a pure substance by itself. Now, if you mix those two together, you basically get salt water, right? And that is what is referred to as a mixture. It's a mixture of 2 substances, water and salt, basically sodium chloride. And again, a mixture is basically a combination of 2 or more pure substances. One thing we'll talk about when we talk about mixtures is even though you mix them together, they still retain their identity. So they're still there. So salt water, even though you may not be able to see the salt at that point, you can do some type of physical process to get the salt back and also separate out the water from it. So we'll talk more about mixtures, I think, in a later chapter. But there's some different types of mixtures. So which of the following contains chemicals: sunlight, fruit, milk, and breakfast cereal? Sunlight pretty much is just straight energy. So it doesn't really contain any chemicals, but the rest of them pretty much do. Fruit contain chemicals that have the same composition and properties. Milk also, and breakfast cereal, for example. Some citrus fruits, for example, have citric acid in it and stuff like that, and they have some chemicals that are in there as well. So chemicals are found in a wide variety of things in different forms, and also obviously in different sort of compositions of what is present. So we might have more of one chemical in something than something else. A couple of other sort of things that are important is, and we'll see it probably in a later chapter as well, is we pretty much have basically atoms. Atoms are really the simplest representation of elements. I'm trying to figure out that word I was trying to think. So atoms are really your basic sort of unit of elements, as we'll talk about when we talk about atoms. They have protons, they have electrons, most of them, and they have neutrons, most of them. And that's sort of your simple arrangement of elements. If you look on the periodic table, that is a list of all the elements that we sort of have. And you're basically a representation of that. When we put basically 2 or more atoms together, we get something that is referred to as a molecule. Now, if we can have a molecule that is the same element, like O2, that means basically we have 2 oxygen atoms that are bound together. That is a molecule because it is 2 atoms that are together. They happen to be the same element, And that would also make this an element as well. We could also have something like CO2, which is basically 1 carbon and 2 oxygen atoms bound together. This is also a molecule because it has 2 oxygen atoms and 1 carbon atom. This is also, though, referred to as a compound. Now, a compound and a molecule are 2 words that sometimes confuse people. Definition of a compound is the combination of 2 or more atoms from different elements. So that's a subtle distinction between something that's a compound and a molecule. For example, this guy, CO2, is a carbon atom and oxygen atoms. Those are 2 different elements, which is why it's a compound. It also meets the simple definition of a molecule because it's at least 2 atoms together. Oxygen here is the same element, so it is only considered a molecule. It is not a compound, but is considered an element because it's all made up of oxygen. So a molecule could be an element. A molecule could be a compound, but a compound can only be when you mix 2 or more different elements together. So that's a subtle distinction, and I think we'll cover it again. So a lot of this stuff in some other chapters in a little bit more detail. But that's sort of the difference between those 2. So a molecule, you could kind of think of it as just really a simple definition of basically 2 atoms. They could be 2 or more atoms that are the same elements, or 2 or more atoms of different elements coming together. Those are all basically definitions of a molecule. But in order for something to be considered a compound, it does have to be 2 or more atoms of different elements coming together, like CO2, which is an element of carbon and oxygen coming together. Any questions on that there? Okay. So another thing that's sort of covered in this sort of introductory type chapter is the scientific method. So these are some of the important parts of, say, the scientific method, which is obviously used a lot in chemistry. Really, a scientific method really all starts with an observation. So obviously you make some type of observation, something happens, and it allows you to sort of raise questions as to, why did you see that? And it will allow you to propose a hypothesis. A hypothesis is really a testable explanation of what you observed. And what I mean by that is usually a good hypothesis is something that you could then go test. So you could run experiments. You could do something to either try to prove what you saw and why you saw it, why it occurred. Then you obviously would go do experiments. And usually when you do experiments, that leads to more observations, maybe leads to you reconsidering your hypothesis and reevaluating it and doing more experiments. At some point, you may end up with a conclusion, and you'll end up with really at the end, one of 2 things. At the very end, you'll end up with either a theory or a law. And that's usually what will sort of happen at the end of a scientific sort of method. Here's sort of a picture version of that. All really starts with an observation leading to some type of hypothesis as to why you saw something occur, something that you could test. You then do a bunch of tests, comes up with experimentations and observations, which may lead you to reevaluate your hypothesis, maybe tailor it a little bit more, and then do more experiments. It may ultimately lead to a theory, or it may ultimately lead to a law when it's all said and done. And what is the difference between, say, a theory and a law? A theory is something that may not be 100% correct every single time, or it may be something that was sort of developed as a result of experiments. And some cases, it can be later proven maybe to be completely wrong, or it may be proven to be wrong in certain areas and things like that. So, for example, there's something known as Dalton's law of atomic theory, and I'm sorry, Dalton's atomic theory, not really law. Dalton's atomic theory, and his theory was good, but later a lot of it was disproven and not be correct. Something like Bohr's model of the atom, or theory of the atom, that theory works really well for something like hydrogen, but if you go to any other element, it doesn't really hold up. So theories are more things that can be sort of revised. They may be later completely disproven, maybe later parts of it disproven, stuff like that. Now, a law, on the other hand, is something that no matter sort of what happens, it always ends up the same way. So the law of conservation of mass. So that is something, no matter what happens, will sort of always happen the same way. We'll never lose mass. We don't lose anything along the way. Conservation of energy as well. We don't lose energy. It can be transformed from one spot to the next, but we always, have sort of a balance in terms of energy. Somebody's losing energy, somebody's gaining energy. So a law is more permanent, if you will. It's less going to be disproven. It always happens that way. While a theory is something that, for the time being, is sort of recognized as being perhaps correct, but could be later found out to be maybe not so correct in all aspects of it. Any questions on that there? Here's some observations. Obviously, you went to visit your friend, sneezes because of a cat. You might hypothesize that maybe she's allergic to cats. You could test it a couple of different ways. Maybe not so good for your friend, I suppose, but if you take the cat away, right, maybe she doesn't sneeze or whatever it may be, or you bring the cat towards them, they start sneezing and itching. So these are ways you could kind of test a hypothesis by obviously coming in contact with the cat or not the cat. Obviously, depending on what you see in that situation, maybe you bring the cat near and she doesn't sneeze, she doesn't get runny eyes or anything like that, then maybe, it's not really the cat that's causing that. Maybe she's allergic to something else, which may lead you to more experimentation, like, hey, maybe it's the perfume I'm wearing that's causing her to do that, or whatever it may be. So these are all sort of observations that lead to hypothesis, also leads to obviously ways that you could test it. If she goes sees, as it says here, another friend that has a cat and she sort of gets the same symptoms, the theory is, she's probably allergic to cats. And again, that's a way you could kind of go through that scientific method. Any questions on the scientific method there? Okay. All right, so some of this stuff we're going to talk about, and again, some of the stuff should be kind of hopefully review, but again, if you want more sort of information, as sort of the earlier question, you are sort of responsible for it, but hopefully some of this is review in terms of math. Again, we should know, when we look at a number, where the place is, the 100 place, the thousands, the tens, and the ones. That's also very important. Perhaps what we were talking about earlier, identifying, where that estimated digit would be. Obviously, as you can see here, the 2 is the thousands place. We have our hundreds or tens and our ones place. When we get into our decimals, we have our tens, hundreds, and thousands place. And again, being able to recognize where these are and which place we're talking about is important. We obviously have a tens, ones, tenths, and hundreds place here in this measurement. Again, the tens place, ones place, tenths place, and hundreds place here in our decimal part. Positive and negative numbers, just a reminder that, typically in chemistry, if a number is positive, you don't have to write the positive value. If it's negative, you typically do need to make sure you put the negative. So you want to make sure that you do put the right sign in. If it is negative, you should keep it. If it's positive, you really don't need to write the positive, obviously, and stuff like that. In terms of multiplication, just a reminder, right? If you take a positive and a positive, you get a positive number, right? Take a negative and a positive number, you get a negative number. Two negative numbers give you a positive numbers, right? So when you multiply those things together, remember to keep in mind the sign, because that might make a difference in terms of the math that you do along the way. Obviously here, 3 times 2 is 6, minus 3 times minus 2. Again, those two negatives will turn into a positive, and in most cases, you probably would not put the positive number there. Here, a positive and a negative number gives us our negative. Either one, as long as we have that negative, it will turn those numbers into negative numbers. When we divide, we do get numbers. And by the way, when we do divide something and you're given an answer, you should give the answer in a number or decimal. So let's just say, for example, you're doing math and you ended up with 1 divided by 4 as sort of your answer, and you circle it. Don't do that in chemistry. Actually put 0.25. So put it as a number. Don't leave anything like a fraction. That's maybe not a bad example, but I have had people leave answers like 325 divided by 1,233 and just circle it. And I go, I'm done. So don't leave a number like that. Make sure you really do divide it out and give an answer. So we don't run into any problems like that. And again, no matter if you're dividing by one negative number, if it's on top or the bottom, you will end up with a negative number when you do that. And again, you don't have to put that positive sign in there. Some of this, I think we remember. When we subtract, right, this is basically our adding a negative number, positive and a negative, basically turns this into 12 minus 15. And we end up with minus 3 here. And again, you do want to make sure you include the negative in this particular case. On your calculator, I had mentioned it earlier, and I think we'll see a picture in just a second, but on most people's calculators, negative button looks something like this. R looks something like this. Do not use your subtract button though, right? So if you want to put a negative in, don't use the subtract button. Again, most calculators will give you the wrong answer if you sort of do that. So here again, just some examples. You can go back through these if you like, and you should get either the positive number or the negative number when you do it. There's kind of a blow up of a calculator here. Again, on a lot of people's calculators, that is what your negative button looks like. They don't have the blow up of the exponent button, but again, the negative button and the subtract button are different, so don't use those two together. Which they have the bigger version of the exponent button. I think they might later, hopefully. And again, in case you need some help punching things in, calculators give people the hardest time sometimes. They have it all set up right, but they just can't punch it into their calculator correctly. So it's good to make sure you know how to kind of punch them in. Take a look at some of these here. Again, it will kind of give you some help, hopefully, on what buttons to push. But one important thing is what we were talking about there at the end. Again, if you're doing some multiplication of numbers and then you're going to divide by some numbers, try not to put it all in at once and then hit equals, because I see it a lot of times people do that. And again, if you don't put parentheses around numbers, you will end up probably with the wrong one. So as I mentioned at the end there, pretty much if you're doing something where you're dividing and you have, a number on the bottom, or multiple numbers on the bottom and multiple numbers up on top. You just want to kind of put everything in at top, like I mentioned before. You can multiply as many numbers as you like. But important, when you get to that last number on top, hit the equals button and then divide by the first number. So you'll hit the equals button, then hit divide. In this case by 123, hit the equals button again. Don't be afraid to hit the equals button a bunch, and then divide by the next number, which would be 22 and then hit that equals button again. So again, you could put it all in at once, but you need to make sure you do the parentheses correct. In my experience, people oftentimes do not do those parentheses correct. Any questions on sort of that there? A reminder as well, percentages. So sometimes we do use percentages. The simple way to, kind of use a percentage as a number. So if I had, say, 57% mass to mass sodium chloride, right, for example. What that means is, assume 100, that means I would have 57 grams of sodium chloride, say, in 100 grams of solution. That's a way you could turn a percentage into sort of a usable number. We take 57 divided by 100, and then times it by 100, you end up with 57%. That's how we could kind of turn these things into percentages. You also multiply by 100, but very common, we'll sometimes need to take a percentage and turn it into sort of a conversion factor. So assuming 100 is the best way to do that, it kind of keeps the numbers the same. Here, if we took 325 milligrams of aspirin in a 545 milligram tablet times 100, it's basically made up of 59.6% aspirin in this case. It's like if you got 50 out of 100 on your exam, you got 50% on your exam, right? So, simple percentages is used a lot in chemistry, and a lot of times we do take percentages and kind of convert them into numbers that are usable. Here's a couple of other ways. Again, 5% red balls means that if you have 100 of them, 5 of them should be red. 50% green means if you have 100 of them, 50 of them should be green. Again, a very simple way to turn a percentage into sort of a usable kind of conversion factor is to assume 100 of something. Any questions on that? We'll see that again later on when we talk about solutions, I think. Now, something as well that's important, and again, if this is problematic for you, you may want to, again, make sure you really do go through this section of the book fairly well. And that's sort of rearranging and solving for equations. We don't do a lot of really difficult, per se, equations that you might have to rearrange, but there are some that you do have to sort of move things to the other side. So a very simple sort of method is when we go across the equal sign, we pretty much have to do the opposite of what it was. So what that means is, for example, if we have 2x plus 8 is equal to 4, and I want to move the 8 to the other side, this is plus 8, which means I need to do minus 8 on both sides. So basically opposite of what it is to move it to the other side. That then gives me 2x is equal to, I guess that was 14. We'll keep a positive number. 2x, it would be equal 14 minus 8 would give me 6 in that case. Now, when I want to get rid of the 2, again, I need to move the 2 to the other side. So what is the 2 doing right now on the left? It is basically 2 times x, if you will, right? So it's basically 2 times x. I'm multiplying. So to get it to the other side, I need to do the opposite of multiplying, which is dividing by 2. So I would need to divide by 2 to the other side. Again, opposites. And we end up with x is equal to 6 divided by 2, which is equal to 3 in this case. The other way you could kind of look at it when you're at this point of 2x is equal to 6 is you could think of these as fractions, like 2x over 1 and 6 over 1. And if I need to move something to the other side, it ends up in the opposite place. So the 2's up on top. I need to move the 2 over here to the bottom. And the 2 goes away, gives me my x is equal to 6 divided by 2, gives me the 3. So sometimes opposite is a good thing to think about when you have an equal sign or you need to solve for something. Basically, you do the opposite sort of calculation to get things to the other side. You could check your answer like it says. Obviously, when we solve for 3, if If we put it back into here, 2 times 3 is 6. 6 plus 8 is 14. So you could check yourself as well. Question on that? We personally won't be doing a lot of solving for x. We most likely will be doing solving like this. Like this particular formula here was known as Boyle's law. And so, for example, if I wanted to solve for P1, what that basically means is I want P1 to be by itself. This again is something you could kind of think about like a fraction, even though there's nothing written there. It's basically over 1, which means what I need to do is when I go across the equal sign, it ends up in the opposite location. So when I do that, I end up with P1 is equal to P2 V2 divided by V1. Now, if I wanted to solve this for V2, again, we could think of it like a fraction. If I wanted to get V2 by itself, I would need to move P2 to the other side. It's up on top. It will end up on the bottom, and we'll end up with P1 V1 P2 is equal to V2. So, this is sometimes a good way to think about it is to think about, opposites is what you do when you move across that equal sign. Another gas law that we'll see later on is P1 V1 over, say, T1 is equal to P2 V2 over T2. And maybe we want to solve for something that's here. Let's say we want to solve for P2. To do that, we need to move V2 and T2 to the other side. And we could take that same approach that it's basically opposites. So to move our T2, it would end up going from the bottom to the top. As we go across the equal sign, the V2 would go from the top to the bottom when we do that. That would give us P1 times V1 times T2 divided by T1 V2 is equal to P2. So especially when we get into some of these formulas, when we get to the gas chapter, opposite locations, kind of think of them as fractions. That's sort of what we're doing. Again, just to bring back to the original one that was on this page, if we were solving for P1, again, if we look at this, P1 is P1 times V1. So to get rid of V1, we need to not multiply, but divide the opposite process. These guys would cancel, and that would leave us with what we got going on and we saw earlier, which is here. So this is definitely something in chemistry we do a lot. Formulas such as these things, you do need to be able to sort of rearrange it to make sure that you can solve for what you need to solve. Now, if you're not good at doing this, if you don't like to do it this way, you could just put the numbers in and just kind of with your calculator do it, but it's basically doing that. You don't necessarily have to rearrange it, but you do need to be able to rearrange it sort of properly. Sometimes it's easier for people to visualize what's going on by just putting the numbers in and just kind of use your calculator and solve it, which is fine. But you should know how to sort of rearrange these equations. Any questions on that there? Okay. Then there's that there. Honestly, we're probably not going to do too much with graphs, but if you want to look at it again, I don't anticipate too much graphing going on in here. So the last little part I think was about scientific notation, which we did sort of talk a good amount on, but again, a reminder, as we talked about earlier, that this is really the general form for scientific notation, and the important part is, as I mentioned earlier, that does need to be a number between 1 and 10, so not 10, 20, or 100, or nothing below 1, but it does need that. We're basically going to be moving that decimal point until we get to that number that is between 1 and 10. And as we talked about earlier, either that number will be positive or negative, this exponent, depending on which way we move it. So again, our 3, 2, 2, 5, we would assume the decimal points here, 1 place, 2 place, 3 places. And as we talked about today, we would keep all those numbers as they are significant. And since we went to the left here, again, positive exponent, and that's opposite if we had a smaller number like we saw earlier as well. We would need to go one place. That gets us 0.01, which is not 1. One more place is 0.1, which is not 1. One more place does give us the 1, 1.332 times 10 to the, we got there, 1, 2, 3, -3. Again, we went to the right, giving us a negative exponent. Any questions on that there? And again, we really do use scientific notation when we're dealing with really large numbers, really small numbers. And as I mentioned before, you don't necessarily have to write numbers in scientific notation. The only time you obviously would have to do it is one of two ways. Either obviously the question asks you to do so, or as we were talking about today, there is sometimes only one way you could get a number to the correct number of significant figures, and that is to write it in scientific notation. Because remember, you basically can control how many significant figures. So if I needed 3, I could write it like this, which would be 3 sig figs. If I only needed 2 sig figs, I could write it like this, which would give me 2 sig figs. If I needed 5 sig figs for some reason, I could write it like this, right? And that would give me 5 sig figs. So the nice thing about scientific notation and sort of what we were talking about today is you can kind of use it to control the number of significant figures in your answer. So if you need a specific significant figures, you could kind of control it by writing it in scientific notation. You could write it either any way you want to basically get you the right number of sig figs. And we don't lose sig figs like we talked about. So again, this number here has 1. That's why when they turned it into scientific notation, it has 1. Same thing here. This guy written like this has only 1 sig fig, which is that guy, which again is why it was written as 1 significant figure there. And again, here's the parts of it, which we talked about. And again, going to the left or the right to get you that. Again, easier way to remember it is larger numbers have positive exponents. Smaller numbers have negative exponents. And here's, again, some examples and tables from your book to reference. Again, if you multiply them there, you do get some of those exponents. And our fractions gives us our negative exponents, which gives us numbers less than 1. And again, here's just some different ways. And clearly, the benefit of sort of writing scientific notation is obviously if you were going to do a calculation with a number like this, pretty good chance somewhere along the way, you might lose 1 to a whole bunch of those zeros, right, as you're doing the calculation. So, it just sort of cleans it up a little bit and make sure you don't lose a lot of zeros along the way, especially with very large numbers or even very small numbers like what we have on the very bottom. Obviously, it would be a pain to write all those zeros doing a long calculation, and also most likely you might lose some of those along the way. And again, here's sort of standard format, which is sometimes called positional notation or decimal form, and scientific notation. Again, basically 3 sig figs here, 3 sig figs on our scientific notation, 2 sig figs, 2, 1 sig fig, and 1 sig fig happening here. So here's, they don't have a picture of the calculator, but these are the 2 buttons we were talking about. And again, you want to make sure that you use those exponent buttons whenever you do a number in scientific notation. And again, if you have maybe a newer calculator, you will have maybe a times 10 to the n button. And again, your calculator will usually have like a little circle thing that you could kind of press, left, right, and so forth. And again, that's the one that if you do have that button, you need to make sure you use parentheses around it. So here's a couple of examples, also should be found in some pictures in your book as to how to properly punch this. At no time, like we talked about, should you be using the multiplication button. You at no time should be using the shift button and the log button to type a number in. And scientific notation, again, when you punch that EE button or that EXP button, that represents the times 10 part of the number. So you don't have to do any part of that. So that's why when they hit 4, and they punch that exponent button, it represents that, and then all is left is to hit 6. Same thing here, 2.5. They hit the exponent button, takes care of all of that. We do have a negative, so that's why they hit the negative button, and obviously a 4 here. And again, these are the common sort of displays I was sort of trying to write earlier as to what you'll kind of see on your calculator when you do that. So when you see something like that, that stands for obviously 2.5 times 10 to the minus 4. When you get an answer in your calculator and you need to write it, you should write it like this. You shouldn't write it like 2.5 e minus 4. That's really not the right way to write scientific notation when you're trying to write it as an answer of a question. You should always write it in proper scientific notation, but your calculator will give it to you with that e. Any questions on that there? And again, a few more examples here. You can, and again, it varies depending on your calculator. You can set up your calculator to do scientific notation. Most of the time, somewhere, you could either do this sort of function, but if you have like a mode button or something like that, and SCI is for scientific notation, you could set it to give you all the numbers in scientific notation. A reminder that although it gives it to you in scientific notation, it doesn't mean that it is the correct number of significant figures. It just means it may give it to you in scientific notation. And again, here, if we're going to write this in scientific notation, we go 1 place, 2 places, 3 places, 4 places. 6.4 times 10 to the 4th only has 2 sig figs, and that's why we have 2 sig figs here. Coming this way, we need to go 1 place, 2 places, gives us 2.1 times 10 to the minus 2. Again, a small number, negative exponent went to the right. These are the 2 significant figures, and that's the 2 significant figures that are there as well. Any questions on that there? And again, that's what that talks about. And which one is correct scientific notation? Again, 1 significant figure, which they all do. We would go 1 place, 2 places, 3 places, 4 places, 5 places, and 6 places in this particular case. And we went to the right, which means we would be negative. So it is this guy here. Remember, negative exponent, small number. And coming this way here, no decimal written, but we assume it's here. So 1, 2, 3, 4, 5, 6, and 7 places. And that's 7.2 to the positive 7, which should be this guy here. And again, only 2 sig figs here, which is why we have 2 significant figures on our answer. Question on scientific notation, our chapter 1 type stuff. Again, not a lot of heck of a lot of material in there that's sort of chemistry related. Again, it's a lot of review, math review, calculator review. Very good to make sure you look over it. Stuff, sort of real, sort of maybe chemistry type topics that you should be aware of. Obviously, scientific notation, how to write it, how to punch it in your calculator correctly. Obviously, stuff a little bit about matter and stuff like that, solid, liquid, and gas. I think we might talk about in later chapter as well. But, scientific method, we probably want to do a lot with that, but, those are sort of the topics there. Any question out of chapter 1? Okay, so that is chapter 1. Again, we will continue lecturing on chapter 2 on Wednesday. Since I kind of used the time to lecture here, if you still have questions on anything, I'll be more than happy to answer those for you. If not, then, you're all good.